I'm not sure where my numbers came from a minute ago. I was obviously not firing on all cylinders when I did that one in class, and I'll have to fix that. Anyhow, 4325 base 5 equals what to the base 3? Well, we convert 4324 base 5 to base 3, we get base 10, we get 589 base 10. Now 589 base 10 converts to base 3. We need a 3 to the 5th, which is 243, and we need 2 of those. 2 of those makes up 486, leaving us 103. Okay, then we have 1 times 3 to the 4th, which is 1 times 81. We need an 81, and to get 103, that leaves us 22. 3 to the 3rd is 27. We don't need any of those. We're only looking for 22. But 3 to the 2nd is 9. To make up 22, we can use 2 of those. That's 18, leaving us 4. And then, of course, we're going to build up the 4, we're going to need a 3 to the 1st, which is a 3, and a 3 to the 0, which is a 1. That makes our 4. So we see we got 2, 1, 0, 2, 1, 1. And our base 3 number, therefore, is 2, 1, 0, 2, 1, 1, base 3. This illustrates probably the easiest way to convert from one base to another. Convert to base 10 and then go from there. As another example, we convert 473 base 8 to base 5. You should do that. I let the class work on this, and then we checked things out and everybody was all right. Okay? This, of course, means what's written down here. We just convert to powers of 8 and add them up, and we get 315. We want to express 315 in base 5. What do we need? Let's hope I did this one right. To make up 315, the highest power we need is going to be 125. We're going to need 2 of those, which makes up 250, leaving 65. To get the 65, we're going to use a couple of 2 to the 5ths. That's going to be 5 to the 2nds. That's going to be 2 times 25, or 50, leaving us 15. And then we'll use 3 5s to make up the 15, and we're done. Of course, we still have to write down the 0 times 5 to the 0. And we see that our number is therefore 2, 2, 3, 0, base 5. This is a short preview of the next chapter. We felt like everybody was in pretty good shape with number systems, although we will talk a little bit more about number systems in the next class. So, this preview of Chapter 4 on number theory just concerns what we call prime factorization, and one quick example of what we can do with prime factorization. Actually, a couple examples. Okay. The first example, first of all, we talk about what we mean by prime factorization. Let's take the number 2354, 2354. Now, a prime number is a number that's only divisible by itself and 1. That means we can't break it down into 2 other whole numbers. So if we divide 2 into 2354, we get 1177. Now, the next prime number that divides into 1177 is 11. We go through a process of figuring this out. 2 obviously won't go into 1177, so we try 3. Okay? We find that 3 doesn't divide into 1177, so the next number is 4. But we're not going to try dividing by 4, because if 4 is going to divide 1177, 2 would have divided 1177, and it certainly doesn't. So we try 5. Okay? Well, 5 doesn't divide 1177 because 1177 doesn't end in 0 or 5. We could try 6, but we've already tried 2 and 3, which are both factors of 6, and they didn't divide it. So 6, no way is 6 going to divide 1177. So we try 7. 7's a prime number. We haven't tried any of its factors because we don't have any, except 1. 7 doesn't go into 1177. divide it and see. 8, we don't need to try 8 because we've already tried 2, and 2 is a factor of 8. 9, we don't need to try 9 because we've tried 3 and it didn't work. 9 certainly won't work. 10, well, we've tried 2 and we've tried 5. Neither one of them worked, so 10 isn't going to work. You notice that what we're doing is we're skipping any number that can be broken down into 2 smaller numbers because we've tried all the smaller numbers. Okay, the next number we try is 11, and we have success. 11 goes into 1177 107 times. Now we ask, well, what's the next number we got to divide by? Okay, we don't have to divide by 2 or 3 or 5 or 7 because we already tried to divide those into 1177 and they didn't work. They're sure not going to work in anything we get by dividing into 1177. So we could say, well, okay, let's try 11. We tried it once and it worked. Let's try it again. Well, 11 doesn't work. 11 goes into 110. 107 is only 3 less, so we can see that 11 isn't going to work. Not only that, but we see that if 11 did work, it would go into 107 less than 11 times. So that the number we get, if we divided this by 11, would be less than 11. That tells us that we're done, because the next number we try would be more than 11. If we divided it, we'd get something even less than that. We've already tried all the numbers up to 11. If we divided this and got a whole number result, that means that that whole number should have divided 107 when we tried it. Since that's not the case, there is no other number that we can divide into 107, and 107 is a prime number. At this stage, we say, okay, we can express 2354, 2354 as 2 times 11 times 107. If we multiply these numbers back out, we'll certainly get what we started with. This is called the prime factorization of 2354. The prime factorization is unique in that this is the only way we can write this number, 2354, as a product of primes. Now let's see how we might apply prime factorization. Let's say that somebody asked you to reduce 231 over 88 to lowest terms. After a while, you might stumble across the fact that 11 divides both of these numbers. But it'd take you a little while. If we go to the simple step of finding the prime factorization of both of these numbers, and usually it's pretty easy to find a prime factorization. Divide 231 by 3, what do we get? We get 77. And then we divide that by 7, and we get 11, and we have our prime factorization. 88 is equally easy, even easier actually, to divide out. And you can't tell it by looking at these numbers. You can't tell by looking at 231 that 11 is a factor. But if we do the prime factorization, it falls right into our laps. Now what do we know? If we got 3 times 7 times 11 over 2 times 2 times 2 times 11, 11 divided by 11 is 1. So that's just the same as 3 times 7 over 2 times 2 times 2, which is 21 over 8. This is in lowest terms because the prime factorizations of 21 and 8, which is what we have here, have nothing in common. If the prime factorization has nothing in common, there are no common divisors, and you simply can't reduce the number.